Right. So point of today is we'll try to review everything to some extent that we talked about over the semester, talk a little bit about the final, which is at 10:30 next Friday in this room, as far as I know. If something should change, I will post it on Piazza. The final is comprehensive, so it'll cover all the stuff in the class potentially. You can have a page of like a cheat sheet kind of page if you want. There's no book or other tools. You shouldn't need a calculator unless multiplying small numbers is a difficulty. Any other questions about the final? Yeah.
Would it be possible so we can use the old one that we created as well?
Oh, I see. Yeah, fine. Okay. 2 cheat sheets. Any other questions on the final? Okay. Right. So I have been working a little bit more on this set of course notes. I thought rather than me going through and making, another one of these things, I will try to kind of update the course notes on the fly a little bit. So I have the LaTeX stuff here. So I'll just have the two next to each other. Of course, at some point, this is meant to be more of a book, right? That has actual good content in it. It's growing, but at least it will be kind of useful bullet items and kind of pointers where you can find more, that sort of thing. That's the idea. I'll teach this class again next semester. No, not next semester. Next fall, I think. It's been approved as a permanent class, and so please spread the word. And it'll be a little more structured next time because now I have a pretty good idea of how what's going to be in the class and all the things that kind of know the subject a little better. Along those lines, I hope you received the course evaluation request and that you fill that out. Just be honest. And there's one more. Let's see. I have this ongoing competition with Dale Reed to have the most reviews, and so he's got 86 and I have 91. So I'm in the lead, but he has so many more students that I fear he's going to beat me this semester.
Percentage-wise, you're far ahead of him.
That's right. Maybe he isn't pitching it as hard in his classes. Anyway. Rate My Professor is a good bit of fun, I think. Nobody takes it too seriously because there's, these hot peppers and all these things. But at the same time, I think it's good to have some kind of public feedback too. Like for some reason, the university feedback is still not public. It used to be for a while. It used to be you could buy it in the bookstore. You could get all the reviews, and that was interesting in a way, but sometimes reviews can be inappropriate, shall we say. So I can see why the university doesn't like to show them, but I think the numerics, I don't know. There's all sorts of arguments in both directions, but it's cool that this Rate My Professor is kind of open, so someone can just take a look before they decide to take a class like, oh, the guy's an asshole. Let's not, right? I think that's good. And then you have to take it with a grain of salt, because there's always some people that are unhappy. All right, let's talk about systems performance then. So the things we need to know, I think I'll just go through this one briefly and try to fill out things along the way. So very important is just having a good grasp on the units and the prefixes, or you won't be able to think about this topic. So make sure that this table is well ingrained. And in fact, I think it's very helpful. It's not really that important to know both of these, but I find it very helpful in just reasoning about things, to know both the powers of 2 and the powers of 10. Okay, and similarly, we need to have a good idea of the sort of computer-specific terms. Without those, we'll really struggle. And there's some typical statistics as well that will be useful to know. Basically, how fast can you load stuff from memory? How long does it take to read something from a disk? And these things, right? I think everyone is relatively familiar with this L1 cache latency, right? And it's not actually that important if it's 3 or 4 cycles, right? But it can't be 400 cycles. If you think of it, if you're off by a couple of orders of magnitude, your whole reasoning will be way off. Right? So I think it's important to have a decent idea of these numbers, at least the right order of magnitude. Okay, so the next, this probably doesn't really apply to the final, but I think we did some exercises on this in the homeworks, and it is a really good process. Like, it really has worked for hundreds of years, and it still works for us. It's important to not just draw a conclusion without testing it. And how do you know if a test is good? It should be able to invalidate your conclusion, right, or your hypothesis. Sorry. So people have been using that in the sciences all the time. We're starting to get where we need that in computer science as well, just because the systems are so horribly complex that you can't reason directly about, oh, it must be like this because that, like it is in math, let's say. You can do that with a small program, but when you have a large computer system, you can't really do it anymore. All right, so then the rest of the class is sort of divided into, I want to say, 4 pieces. There's the tools and techniques, which is basically all the profiling and all of the various measuring things in the system, timing, how fast things are going, let's see, and various sort of more advanced ways of inserting code either in the kernel or in the user program to learn things about the program. So there's a lot of those. Maybe we'll go through them. Yeah, we'll go through them shortly. And then there's single-threaded program performance. And there we're mostly thinking about concurrency in the context of a single thread. Right? Everything is concurrent these days, or it wouldn't run fast. So you kind of have this single thread appearance, sequential execution of operations appearance, until you start looking at the timing, at which point you learn that, oh, in fact, they're all running parallel one way or another. So single-threaded is about out-of-order execution of instructions. It's about the memory hierarchy, caches, all that sort of thing. And then there's multi-threaded performance, and there things are a little different. You know, you can't just multiply by the number of threads. Sometimes you can. But we need to understand under what conditions can you just multiply by the number of threads and get the right performance number. Usually there's some coordination between the threads, and that can really slow things down. So there's contention over just cache lines. You need to understand false sharing, that sort of thing. There's contention over locks, very critical, and then lock types are very important there. Choosing the right lock type for your application, for the system you're running, can have enormous impact. Probably memory allocation. We haven't really talked much about that, but I think memory allocation is another important aspect. We've talked some about it, like using stack memory versus global memory versus using the heap. I think one thing that I kind of skipped, maybe inadvertently, is that there's actually several different versions of malloc as well. The one malloc that's there in Linux or in GCC by default is called PT malloc. It's pretty good. For every thread, you end up, if you have a lot of contention, for every thread you end up with its own area. So it's actually like n different malloc areas, n different heaps, each managed by a separate thread, but that's not always the best choice. At some point you might run into, you won't run into that in the final, but it's worth keeping in mind that the GCC malloc is certainly not always the best choice. And there's lots of options. Okay, so single-threaded, right, multi-threaded, sorry. There's the performance aspects, which we just mentioned briefly, and then there's the correctness aspects. So we want to worry about ordering of operations actually now looking out of order. Right? With a single thread, everything executes out of order, but you can't tell because the CPU kind of fixes it. But when you run things in parallel on different CPUs and they observe each other's work to the extent that this can be observed, then you can start seeing the code of the other CPU actually running out of order. And that can sometimes create severe consistency problems. So you want to try to constrain that when it's necessary. But of course, that out of order execution is what makes things go fast as well. So some kind of trade-off there. We definitely want to know what guarantees are provided by the CPU and how we can constrain it further. Of course, there's the fences. Like an M fence is one way, kind of a heavyweight way of restricting out of order execution within one thread. And then there's locks, of course, and barriers and condition variables. Okay, so I think that is the sort of the high-level view of the multi-threaded. And then let's see, so now we have tools and techniques, single-threaded, multi-threaded, and then there's the data parallel execution. So this is where we get into vector-type computations or vectorized code, and also the GPU stuff. So sort of what the model of vectorized code, it's important to understand what vectorized code does, how it makes things go faster, right? The normal code, under what conditions you could expect it to go faster, right? And to some extent, what the compiler can be expected to do with respect to vectorization. And then similarly on the GPU, we want to have a good idea of the programming model, the expectations on like when can a program run fast on a GPU? Well, it's mostly when you can have an insane number of threads that all don't interact with each other. Like that's the ideal situation. You have 100,000 threads and they all operate completely independently. Then you can be assured that the GPU will run fast, unless perhaps you're always loading new memory. Like if you're doing mostly memory moves and not actually doing much with the stuff, then maybe you're better off on the CPU. So I think those are the 4 pieces at the high level. Let me make sure. Yeah. So after that, I think we want to kind of try to dive into each one of them in a little more detail, but I'd like to have discussion on anything and everything. These things can get really boring otherwise. So just stop me anytime and we can spend the rest of the lecture on that. I mean, this document is available on the website. You can just download it and whatever. I will upload whatever changes we make here after lecture. Okay, so let's see. So for the tools and techniques, we definitely want to know about sort of high-level high-level resource utilization methods. Like how do we measure this, and what does it mean? Right. So CPU time, and what's the difference? Oh, this is a good one here. Come back to. I guess it's not quite here. Okay. Time. Right, so the time program. What is the difference between user time? Let's see, what are the things? It says wall time or real time, I think. And it says user time, it says system time. So, here the real time is what's on the clock, of course. User time is what time we spend spinning on the CPU, where actually the program itself is operating on the CPU. And then there's system time, where the program is busy, but it's busy in the in the kernel. It's not actually running user code. These other things are various tools for measuring how much of the total CPU resources are being used. I think it's very important to understand the difference between like one CPU being used 100% versus all the CPUs, and when can you expect that to actually make a difference. So in order to use multiple CPUs, you have to have multiple threads. One thread can't run on more than one CPU at the same time. Something similar is true for locks, right? In order to have use multiple CPUs at the same time, you actually have to have more than one critical section, like more than one lock, if you spend a lot of time in critical sections. It comes back to this Amdahl's law too, that the speed up that we can get out of parallelization basically depends on what fraction of the program is spent in serial execution. Okay. So memory utilization, something similar. This proc file system is actually quite interesting. If you've taken the OS class, you probably have an idea of how it works. But it isn't actually real files. Like they're not on disk anywhere. If you say cat proc meminfo, all that happens is you get a read system call, and the kernel sees, oh, they're trying to read this file, but that's not a read file. That's not a real file. So it'll just put some characters in the buffer. Like it'll sort of sprintf some characters into the passed-in buffer, saying how much memory you're using at the moment. So there are all these pretend kind of virtual files. Very cool stuff. There's a lot under /proc. If you haven't taken the OS class yet, plan to take it. It's good stuff. It'll probably be taught in the fall next time. Okay, so there's some other similar things for I/O which we haven't played much with. Those are not going to be important on the final, but definitely take a look at these. If you want to learn about what the disk is doing, right, or what your network card is doing, that's also important if your program is disk intensive or network intensive. Timing your programs inside of a program, I think one very common way to do it is to use this get time of day. That gives you a sort of a seconds and microseconds sort of measurement. It's accurate and good stuff. If you want higher precision, and I'm not sure that it'll be as accurate necessarily, but you get higher precision, meaning it'll tell you in a very small in a very small unit, right? It'll be cycle by cycle. It'll say how many cycles you spent executing this one operation. Right? That's high precision, but the accuracy is like, oh, and how much could it be off by? And I think with RDTSC, this cycle precision measurement, you probably don't have much higher accuracy, but it's very handy. So this little tool here, _RDTSCP, is this intrinsic function. Basically, it translates into a single instruction, x86 instruction, which returns the number of cycles at the moment. You do it again, you get another timestamp, you subtract the two, you see how many cycles you've spent. It cannot be reordered. It's the idea. Like the P version cannot be reordered, but from what I can tell, it's not that you get precise measurements anyway. It'll. I'm not exactly sure how this works, but you should expect to have relatively large errors. So it's better to measure a million times around a loop rather than one instruction, right? And then kind of divide by a million. Generally speaking, this is true for all measurements. There's noise everywhere. You want to try to make many measurements and take an average and maybe measure the standard deviation, as opposed to just taking one measurement and saying that's what it was. Because all sorts of things can happen. Right? You could have an interrupt during your execution here. And then an interrupt that could use up 1 million cycles. And now you think that your function takes 1 million cycles, whereas in fact it only took 500. And yeah, always try to make lots of measurements and compute averages. Something related to that is if you're running an experiment, you want to see, oh, how fast does this program run? It doesn't make any sense to measure for a program that only takes 10 milliseconds to run. If you say time and that program, run it for a little while, the sort of setup time to start up the process, to load something in, to make sure you get scheduled and so on, all of that could be much more than the execution time of the program. So you want to make sure that any experiment is at least a second long. That's sort of a very rule of thumb sort of thing, but aim for experiments that take between 1 second and 10 seconds. If you have an experiment that takes 10 minutes, you're not going to want to run 100 of them, right? So you can't take a good average. But if you have something that's less than 1 second, you can do many of them, but each one of them is going to be very noisy. So, good trade-off, somewhere between a second and 10 seconds, just what we usually go with. Okay, watch out also that it takes a lot of time to just record the timing. So if you measure how long it takes to go around a short loop, and then you printf that, chances are the printf takes much longer than the loop. So I suppose as long as you printf after and you don't care about anything else in the program, you're probably okay. But generally speaking, all that printing will get in the way. It can slow things down by millions of times. So definitely watch out. One good way to address it is to store your values first in memory, in a little array, right? And only print every now and then, maybe even just print an average of them. One thing to really watch out for if you do that is where you're storing your intermediate values. Now, whether that's an array or just a single integer perhaps, it's a good chance if you have a multi-threaded program that you put your logging variables for the other threads right next to it. And now they're all sitting on the same cache line, you have false sharing, and now your logging actually slows down your program again, really a lot. Alignment there is a really good way to, this is not correct syntax. Let's see. Oh, I'm in the wrong there. Where is it? Yeah, it goes attribute lines. Don't ask me why. I think it's there. And the backslashes are just to make LaTeX happy. There we go. All right. Definitely worth watching out for, at least. How do you log in addition to how do you measure? There's, of course, doing this manual measurements is a lot of work. And if you don't really know what you're looking for, then it's not a good idea. It's really good if there's this one function and you want to see, and you know that that's a likely place where you're spending time, or maybe you're splitting up. You say, oh, this function, is it the upper part or the lower part of the function that's taking a lot of time? It's really easy to measure it manually, and often a good idea to just printf things. But if you're looking at a larger program and you're trying to get a good handle on what it's doing, you probably want to use profiling tools. The main one that we are interested in Linux would be perf. Perf is really, it's continuing to mature into a fantastic tool. And lately it's using this new, not an architecture, what's it called? Framework, this Berkeley packet filters. Extended Berkeley packet filters. Basically the idea is you pass in some bytecode to the kernel saying these are the things I want you to do, and because it's in a certain bytecode format where you can't express bad things, like dereferencing arbitrary pointers, the kernel knows that you can't access places, you can't do things you aren't allowed to. There's no way to express an illegal program in this BPF format. And so the kernel will compile it, JIT compile it into actual executable code and run it for you in supervisor mode, which otherwise would be ridiculously dangerous. It's like having a built-in rootkit that just comes with the kernel. But because of this Berkeley packet filters, the rootkit, yes, you get to execute as root. You can and run any program you want as root, except for bad programs. Those can't be expressed. So that's really cool to be able to do that sort of thing in the kernel, and Perf is quickly moving over to using that for all sorts of neat tools. There's two main functionalities provided by Perf. It's all based, initially it's called Perf because of the performance counters, the hardware provided in the CPU. So the way those work is you can, if you're now supervisor and you have all sorts of permissions, you can tell the CPU that, oh, I'm interested in performance counter so-and-so, some number, and it'll start counting that number for you. And then you can also say, oh, and when you reach this number, in fact it goes the other way around, it says, you say, like, tell me when 10,000 of these events have happened, and then an interrupt goes off. So Perf is a command line tool to kind of get access to that sort of counters, and you can do fantastic things with it. Two main things that the command line tool does is sampling, where basically it'll tell the CPU, right, after X cycles have happened, then trigger an interrupt, and then there's some kernel code that will collect data about the running process. Right? And the main thing that we collect is the stack trace to see what we were doing. So that's the sampling way of using Perf, and then the other way is just counting. So you say, oh, just tell me how many cycles were spent. Right? So now run this program and count how many cycles we're spending, and then it just outputs it in the end, or perhaps at given intervals. Right? So you could tell it like, oh, every so many cycles, I want to know how many of this some other event have happened. But you could also tell it to sample the processor, sample the process every so many events of an arbitrary set of events. Like there's a very large collection of different events you can sample from. So the most common thing that we want to do is probably to sample what we're doing. So just over time. So what are we spending most cycles on? So here we're telling the CPU, right, that, oh, tell me after 100,000 cycles, have an interrupt. And so it'll keep doing that. Interrupt every 100,000 cycles. You get a little sample that's recorded in a file. And at the end of execution, there's another piece, perf report, that takes all of those samples and compiles an aggregate of what was all the things that the program was doing when those interrupts went off. So what can we do with that? Well, one very common and popular thing is to open it up in this hierarchical view and kind of see, oh, you're spending 25% of your time in this one function. Its function and all of its children, say. That gives you a good picture of where it's time to start optimizing your code. Of course, we always want to profile before we do any optimization, because it's really easy to waste your time doing optimization where it doesn't really matter. Okay, so that's how the sampling works, and then how the counting works is basically at the end of the execution, it'll just read the counters. It doesn't need to deal with these interrupts very much. Call graph here is very important. How does the kernel know, or how does perf know? In fact, I don't know if the traversal is done by a kernel piece of code or in user space. But in any case, the call graph is collected. Call graph being this function called this function, which called this function. How is it collected? You traverse, ideally you would traverse the stack. The stack has a frame on for each function at the moment. So we're in some function which was called by some other function. The frame on the stack above will be for that function, and so on. So how do we know where to go? Well, depending on how you compile your program, there may be frame pointers. A frame pointer being in EBP or RBP. There's just the address of the beginning of the frame. Now that's good for the current frame, but then just or somewhere around there, there's also the address of the previous one and the previous one and so on. So that now you at least know where does the frame on the stack start. And how do we know which function it was? Any ideas? How do we know which function a stack frame belongs to? Yeah.
RIP.
It's an RIP for the current function, exactly. And for the previous function?
The return address.
That would be return address, exactly. Yeah. So that's one way to do it. Unfortunately, it's kind of slow. If you have a function call, if every function call has to push the frame address or the base pointer of the frame onto the stack, that's an extra write. Every write is going to be at least 4 cycles or a latency. Maybe it is filling up the stack. No, not the stack. The store buffer to some extent. It'll slow things down a little bit. So clever compiler writers decide to not include that base pointer in the stack frame, and therefore go faster, but then you can't get the stack trace. So the workaround for this is this dwarf. It's an extension to the ELF file format at the very end of it. If you compile it with debug headers and dwarf headers enabled, then it'll say for every RIP what was the size of the stack frame there. So for every address in the whole program, it'll know like, oh yeah, when I'm at this line in this function, I've already allocated this many bytes onto the stack, always. So now we know from the RSP, the stack pointer, we know where the beginning of the stack is. And so now you can kind of go back using those offsets. You always have the correct RBP given an RIP, and you can traverse the stack frames that way. So because it's so common to compile without the frame pointers, the call graph equals dwarf is a kind of more reliable way to get it. Important stuff, yeah, here. Otherwise you can just compile with a no omit frame pointer, and that'll be okay for your program. Still not going to be okay for libc, which you're probably using, or all sorts of other dynamically loadable libraries that are part of your program. If they weren't compiled with it, then there still won't be any frame pointers in their functions. Okay, yeah, what does this -g do? We almost always have symbols, like where is the beginning of a function, that'll almost always be there in your binary. And where are the global variables, sort of thing. Those are just normal symbols. They're not considered debug symbols. Debug symbols also have, for every line, for every piece of assembly, or instruction of assembly, it'll know what was the corresponding line in the C program. So now you can say, oh, break on line 15 in this function, for example. It's the debug symbols. There's probably more to it. Yeah, things like you would also know the names of local variables. That disappears. Normally that disappears in assembly. It's just sitting in some register or whatnot. But with debug symbols, you can refer to them. Okay, we talked about eBPF. That's good stuff. This is another way of doing the what perf is doing. Like you get access to more performance counters, some kind of a lower level thing if you want to do performance counter measurements. Probably not that important for us. Right, we had a quick look at this perf probe, which basically allows you to define new events, and then you use the perf tools the same way. Yeah?
In the text there, it mentions a flit. What's a flit?
Sorry, where does it say that?
Flits that traverse a QPI bus.
Oh, I see. Yeah. So this is very low-level details, right? The QPI bus is the interconnect between chips, and they have a sort of a networking protocol going on between them. So a flit would be an individual write that goes across that bus. I think that the bus is a parallel bus, like 64 bits going in parallel or something like that. I would imagine that a flit is one of those, but I'm not sure. And then there will be acknowledgements and things going across this bus. Like there's stuff that we don't get to see, but you can measure some of that with this tool. Right, and this is another cool little extra. Right, so perf record is the thing that does the sampling. Perf stat is the thing that does the counting, right? And it doesn't produce a file. Perf record, you get this file of lots of events lots of stack traces that were there when a certain event went off. Perf script just prints out all of those stack traces. And that can be really handy sometimes if you just want to see sort of a sequence of what was the program doing when all these events went off. Right, and we had I'll put in, for all of these, I think I'll just put in whatever I was using in the demonstration yesterday. It's just kind of handy pieces. Whether I can make a sensible final question about that, I don't know. Maybe. Okay, there's also this call tracing. So many of these things are kind of related, right? But call tracing is this idea that the kernel will tell you whenever a system call happens. So the program is running unencumbered, but then you can ask the kernel to report what system calls are made. So there's a little bit of extra code in the kernel that kind of comes on and off if when necessary. I would imagine that this is also implemented with eBPF these days. It'll be extra work for the kernel to always be looking for, does anyone want to know about this system call? Right? Much better to just inject code when someone is looking, to inject code in the system call itself, to report it, and then remove the code when no one's interested anymore. That's the sort of thing you can do with eBPF. In any case, strace is really good for that. Now you can see all the system calls that happen. ftrace is another thing if you want to see what's going on in the kernel. If you're doing, if you've determined that, my program is really slow because the kernel is taking too much time executing these system calls, then ftrace will tell you what is it actually doing in there. You can take a look at the source code, which is available for Linux, of course, and get an idea of why is it spending so much time in here, and maybe you can change your program based on that. Okay, and then there's program instrumentation. This was the pin tool we played with last time. It's to some extent similar to eBPF. eBPF is only for kernel stuff. It only makes sense for kernel stuff. It's when you don't trust whoever's giving you the code, you don't trust them, and you still want to run them in your context, in the supervisor context. With the pin tool, you're doing it, you're trusting yourself, it's fine. So then you're just modifying the program and running it. So in that sense, it's about the same thing, but it's program instrument. Yeah, it's the same thing in the sense of program instrumentation. eBPF is necessary to make it safe in the kernel. Okay, so actually before we move on, let's take some questions on tools.
Can we do a miscellaneous question?
Yeah.
So for the QPI bus, if you have 3 sockets on the CPU, does that mean you have 3 buses across all 3 CPUs that have to follow this protocol?
3 sockets on the motherboard, you mean, I guess, right? I have never heard of such a thing, but 4 is common. So
Yeah, I was just wondering because the 2 seemed, I guess, kind of simple. I was just wondering how complex it can
yeah. So Intel makes 4 different versions of their chips. One being just single, 4 motherboards with a single CPU. There is no QPI bus. And then the one for 2, that's a very common configuration. So there's one set of bus pins on the CPU. But then the next more common is the one that can support more. So now you have 2 buses, one going that way and one going that way, let's say. And so it makes sense. You can make a sort of a square out of that. That's a good topology. But if you want to have 8 CPUs, it starts being a very long circle, right? If you only have 2 outgoing links. So if you want a really large system, they have a final version which is much more expensive, which has 3 QPI buses. But then you get a nice fan out. So you could have a relatively large system and not have too many hops to get to the processor you want to talk to. I think the largest I've seen is a 64 node machine. So you'd have 64 chips on one. It's not on one motherboard anymore. There are no motherboards that big, right? But you can kind of stack them. But those are not within the reach of academic budgets unless you get a donation from someone.
Yeah.
4 is still reasonable. 2 is very common. And if one of you decides you want to do an interesting research project next semester, I just bought a little cluster of 4 of these machines with 2 nodes on each. And we'll try to do some little performance experiments on high performance clusters. Okay, so for single-threaded performance, the most important aspect of single-threaded performance, I think, is memory accesses. So whenever you try to load something from memory, if it's actually in DRAM, it'll take you forever. Well, it'll take you hundreds of cycles sometimes. In order to make a program run fast, if it's accessing memory, you want to try to do something else while you're waiting for that memory load to finish. Otherwise, you might end up, you wait for 200 cycles, and then 2 cycles later, you find out, oh, I need to do another load. Right? So now you wait for another 200 cycles, and so on. So the sort of the general idea of CPU design in that regard has been to run instructions out of order. You start your load, and then you run some more instructions, assuming those instructions don't require the input from the load. Of course, that will often be common. You'll often have a load and then add, let's say, add the value from the load. So in order to get beyond that, they add this large instruction reordering window. So now you can consider hundreds of instructions at the same time, or 160 or so. And you'll find some instructions in there that don't depend on that one load. And then you can get some more work done. Another important aspect that I noticed some people didn't realize in discussions is pipelining. If you have one instruction that takes a long time, you can often split it up into many smaller pieces and run one little piece at a time. That's called pipelining. So in processor design, usually you need to finish an operation or a piece of an operation per cycle. How fast you can run your cycles depends on how long these operations are. If you have a divider circuit in there, and division takes, to finish all of the various stuff for the division, if it takes a microsecond, let's say, then you want to finish your division so you can run the next instruction within a cycle, then the cycle has to be a microsecond, so now you're running at 1 megahertz. That's problematic, at least for modern CPUs. 1 megahertz, that's what processors ran in the late 70s, let's say. And then you want to go faster than that. Now you try to divide up that operation into many pieces. Maybe we divide it into 10 pieces. Each piece 100 nanoseconds. Now you can have a cycle time of 100 nanoseconds. I run at 10 megahertz. But of course, it'll take 10 cycles to finish the job instead. What's really nice about this is that you have 10 pieces. That's another aspect of the pipelining. So now you start the first piece, finish that in 100 nanoseconds, and then comes the next, and now you start running the second piece. But the operational part that ran the first piece is now free. So you can start another division job after 100 nanoseconds. So, and then after another 100 nanoseconds, you can start another division. So now you're running 10 divisions in parallel. It's another kind of parallelism that's been there for ages in CPUs. So when we say, oh, the latency for a certain operation is 5 cycles, that doesn't mean that the execution unit is occupied for 5 cycles. Probably it'll be occupied for 1 cycle, and the next cycle it can start another one. So you can run 5 of those operations in parallel. Generally speaking, that'll be what's happening. But of course, you can't start you can't run any instructions that are dependent on the output of this instruction until it's finished. So that's the that's what the latency is for. You need to know if I have a sequence of operations that all depend on each other, how long is that going to take? That'll be the sum of their latencies. Yeah.
Is it usually the case that the pipeline is like 5 stages deep? Or
Intel pipelines go as deep as 13 to 16, depending on the exact architecture, I think.
so for the exam then, like, I guess approaching a question which might involve a lot of pipelining, could we just assume that it's 5? Or is there like a baseline metric we might be able to look off of?
You wouldn't have to worry about it. I think you could think of it this way. There will be the depth of the pipeline will be the same as the latency of the operation. Right? So in that sense, you can start one every cycle. Right? That's almost always the case. I think for division it can't be the case because the division was 120 some cycles. I can't imagine they have 120 stages for the division. There's something else going on there. Actually, Intel instructions aren't what they seem. Right? So you have some instructions like CPU ID, which looks like one instruction, but then it gets into the decoder, right? Remember the architecture diagram, there's a decoder at the very beginning, and it'll explode that into like 100 micro-ops. And each one of those micro-ops needs to run on one of the execution units. So it's sort of a high-level language. The assembly that we write is a high-level version of the actual micro-ops that the processor eventually executes. When I got my undergraduate degree, there was still sort of a tension between CISC and RISC, the complex instruction set computers and the reduced instruction set computers. The idea being that with RISC, each instruction can go much faster. And that's nice, you can get a high clock frequency. With the CISC, you don't need so many instructions. And that's nice because now, if you don't need to run so many instructions, that goes faster, so you don't have as much code bloat and that sort of thing. But Intel kind of put a stop to that whole conversation by just putting a little compiler in the CPU that takes the CISC instructions that they have into RISC, that's the microcode. So now they get the best of both worlds by applying some more silicon to it. And they keep shrinking the silicon, so that's okay. Okay, so lots of good stuff in this Agner-Fox materials. Both the instruction tables, which I kind of like looking at every now and then to have an idea. Of course, it's different for every architecture out there. Like every new version will be slightly different numbers, but the rough thing, it kind of stays consistent. There's also a really good manual for optimization by this guy, and I think there's a link to that somewhere in this document. Definitely worth looking at. Another thing to watch out for is this the TLB, the translation look-aside buffer. So the first time you access memory that you haven't accessed in a while, there's this whole page table hierarchy, right, that says for this virtual address, what's the physical address that where we actually want to read from? And the CPU needs to, so you say, oh, load from A, right, address A. Now the CPU needs to figure out, oh, actually, where is that in real memory? Which chip is that, so to speak? And that can be a question of dereferencing 4 pointers throughout the page table hierarchy before you know which address to even read from. And that can take quite a bit of time. There's the translation look-aside buffer, that's a page table cache. In every CPU you have a page table cache so that subsequent accesses to similar addresses, to at least to the same page, will be much faster. Right? Those are less than a cycle sort of cost. But it can be hundreds of cycles the first time, depending on how the page table, where the page table is. If it's in RAM, then that could be really expensive. Okay, and right, instruction level parallelism. There's the out-of-order execution. There's the fact that we have multiple execution units, which is, also provides some parallelism there. And of course, then the pipelining we discussed. Right, sometimes you can get better speed if you kind of reduce the number of dependencies within the code. So here is an example of optimized and unoptimized code. So here we're multiplying RSI. Let's see. We keep multiplying the same thing. But this multiplication, I think it ends up over here. The result ends up in RSI. So this multiplication depends on this one finishing. That's a long wait. I think it's in the order of 5-10 cycles. So now we're going to wait a lot before we get to run the next one. But this one here can run in parallel because it doesn't depend on RSI. So this is unoptimized code because it's two different operations here. But then an optimized code realizes that, oh, we can actually do these multiplications in any order. So let's reduce some dependencies. Here's the one without dependencies. So we're kind of multiplying. Actually, it's kind of a bad example. I think you can do much better. But it could be the latency of this multiplication is short. Okay, so if you want to prevent out-of-order execution, of course, there's the mfence. That's the big one. sfence and lfence usually aren't that important because normal loads and normal stores are in order anyway, but there's some special loads and stores that are not guaranteed to be in order. They're the non-temporal loads and stores. Those are worth looking out for. And if you use those, then you will want to combine it with lfence and sfence to preserve order. Right, the memory hierarchy, we need to know about the relative sizes and speeds of registers, L1, L2, and LLC. Registers being nothing like memory, right? Registers don't have addresses. They have names. Those names actually correspond to indexes, temporary indexes into a register renaming buffer in the end, but certainly it's got nothing to do with addresses. Whereas an L1 cache represents, it has a 64-byte copy of some chunk of memory. It may be an out-of-date copy sometimes, and that'll look like you have like your load got reordered. If you read from that, it looks like your load happened earlier than it actually did. It may be the most recent version, like maybe you modified it. So now the memory is out of date, but your cache line is the one that is holding the most recent value. And the CPUs kind of keep track of this. Like they make sure that you don't have two CPUs writing at the same time to the same cache line. But in terms of what value those writes were based on, that's up to your own code to make sure that you have consistent values. That's where we end up needing to use either atomic operations or locks to guarantee correct operation. Okay, yeah, so memory contents can also be written out to disk. If you use way too much memory, then the OS oversubscribes the actual available memory on the system, then it'll write out some of the pages to disk, and then you'll end up with dramatic performance degradation. You want to refresh on cache associativity as well, just to see what the effect is of writing to regularly spaced addresses. That random accesses, you don't almost ever have to worry about cache associativity. But if you're doing accesses every 256 bytes, it could become important. If you're doing accesses every 4 kilobytes, 4,096 bytes, right? Certainly it becomes very important if you're doing it frequently, right? And then there's this speculative execution that the CPU actually, in order to go even faster, and if it doesn't have any instructions to run at the moment, it's just waiting for some loads or for some other thing, then it'll try to find some instructions that maybe it'll run in the future. It doesn't know it'll run it, right? If you just have a sequence of instructions with no branches, yeah, it'll have the whole window and see there's something good to run in here. And if you can't move the window further down, well, that's it, then it'll stall. But then eventually these instructions at the top finish, and then you can move the window down. But oftentimes, you'll have a small part of the window, and then there's a branch. And you're waiting for the comparison to finish so you know whether you'll go this way or go that way. And the CPU doesn't want to wait, so it'll say, oh, I think it'll go that way. And then just run as if that's the case. And then when the result comes in of the branch, it might say, oh, that was wrong. It'll have to roll back all the work it did up until that point and then start going down the other branch. This is enabled by the store buffer. None of the, or most of the effects of all those instructions that we ran are only visible, or only like stored in some sense, through the store buffer where you're writing to RAM. The rest is internal state on the CPU, easy to reset. So thanks to the store buffer, we can kind of keep all those moves to memory until we know that, oh yeah, we were supposed to go this side of the branch. It's really nice. Of course, when we do make an incorrect branch prediction, there's a cost involved. Rolling back isn't cheap, and of course we missed all of those instructions that we wanted to run. I think I need to go in a little less detail. With the compiler, it can do all sorts of optimizations. It's important to at least have an idea of what it might do so that you know what to look for when behavior starts becoming a little weird. Usually, you can't tell on a single threaded execution, you can't really tell that things got weird, except that it ran much faster than you thought it would. Right? Or two different programs that look extremely similar. One runs much faster than the other. Usually that's because the compiler realized something clever. Right? Oh, I don't even need to run this entire loop. Just throw it away. You can get really strange effects in a multi-threaded program with compiler optimization, because you think that your code runs in this order, but in fact the compiler turned everything upside down and runs in a different order, and you can't observe that from a single-threaded execution, but from multi-threaded you can. You can prevent some of that using a memory or a compiler fence like this, or sometimes using a volatile variable. Global variable will prevent the compiler from kind of eliminating loads and stores to that variable. And restrict is a way to sort of assure the compiler that these two pointers don't point at the same thing. And that allows the compiler to do more kind of optimizations. So it goes the other direction. Be aware that structs are not guaranteed to be packed. So if you have a struct with a character and then an int, you would think that that's a 5-byte struct, but it could very well be an 8-byte struct. It puts some padding in between the character and the and the int to make sure the int was 4-byte aligned. Compilers do these sort of things. You can tell the compiler you really want it to be packed with an attribute packed. And you can also say variables have to be aligned at a certain alignment within the struct, I think, with a line. So you can say, yeah, this third element of my struct needs to fall on a 64-byte boundary. Make that happen. As long as the struct starts on a 64-byte boundary, and there's no way to guarantee that. Because you can always cast a pointer, any pointer you want, to struct type, and then you don't know that that's going to be on a 64-byte boundary. Okay, multi-threaded programs. You want to be well familiar with the pthreads API, sort of the execution model, in particular the create and the join and the locking and unlocking barriers and condition variables. We want to be familiar with the order of operations guaranteed by the x86 CPU, in particular the total store order and total load order, and also what happens with atomic operations. Usually loads and stores can't be reordered with atomic operations, and atomic operations themselves are serializable. Serializability meaning you can take the set of outcomes, like the whole execution, and it's possible to come up with an execution on a single CPU that would have produced the exact same result. So a strict order of all the operations of all the various CPUs. Generally speaking, that is not the case. Executions are not serializable. Multi-thread executions are not. If you put an M fence in between every instruction on all your CPUs, then I think it does become serializable. Yeah, I think so. I can't swear to it. Okay, when we're using locks, of course, locking is expensive. Acquiring a lock can be relatively expensive, even if nobody wants it. If someone else wants it or is holding the lock, then it can get hideously expensive because you have to wait until they're done with it. Whatever they're doing in their critical section could take a very long time. You're better off if you have more locks in that regard. If there's more locks, protecting, of course, different data structures. You can't have two locks protecting the same thing, then the locks are useless. But if you divide your data structure up into many pieces and each one is protected by its own lock in a safe way, then that's called fine-grained synchronization. And the fact that you have more locks usually will provide more parallelism, allowing more of your CPUs to run at the same time. That can be much better. Then again, it's not cheap to acquire a lock. So if you're running single-threaded, or if the other cores aren't at this point interested in your data structure, in the same data structure, then you're spending a whole lot of time acquiring and releasing locks unnecessarily, and that can get quite expensive too. So there's a trade-off there between the overhead of fine-grained versus coarse-grained and the extra concurrency that you do get. I guess you would find that the scalability of fine-grained is better, but the raw single-threaded performance of coarse-grained is much better. Consistency-wise, they're the same as long as you protect your data structures correctly. Another sort of cool hybrid between the two is this hashed array of locks. So you have, like, instead of millions of locks, maybe you have 16 locks, and you say for each item, you just kind of maybe hash the pointer and decide, yeah, I'll use lock number 5. So now you have fewer locks. You don't need to deal with the cost of allocating all these locks, the extra memory, and the locks might even already be in your L1 cache, making things faster, but it can be quite dangerous because whenever you have multiple locks, you have to acquire them in a certain order to make sure you don't get a circular dependency, in which case you get deadlock. And if this hash doesn't preserve that order, and you're acquiring multiple locks at the same time, you're probably going to get a deadlock. It's an interesting kind of corner case. Take a look at barriers and condition variables. Make sure you're familiar with that. By ad hoc synchronization, we just mean any code that doesn't use pthread synchronization operations. It's using atomic operations or non-atomic operations to create synchronization in some other sense, and the standard way to do it, I mean, like the most common kind of ad hoc synchronization you'll see anywhere is this stop variable. Like you say while not stop, right? Or while keep running. And then main thread at some point will set it to 1, and then everything stops. That's ad hoc synchronization. It's perfectly fine. Can be a little bit more difficult to reason about, but it's often quite practical. Right. So definitely watch out for false sharing. False sharing being the idea that two variables that don't seem to be the same variable sit on the same cache line and therefore behave performance-wise as if they're the same variable. Correctness-wise, they don't. It's not that you would get an accidental race condition on two variables that are next to each other on the same cache line. It'll work just fine. But the CPUs will be fighting over the cache line, going back and forth unnecessarily, and that can really slow things down. In terms of lock designs, be aware of the difference between a spin lock that keeps spinning and a sleep lock that asks the kernel to put the thread to sleep until the lock is available. There's there's the ordered and unordered locks, a ticket lock being the most common ordered lock. The trade-off there between ordering and not ordering. Ordering is nice because you have some sort of fairness, some guarantee that your thread will actually get to the counter in the butcher example, right? At some point, you can see that you're making progress. And an unordered lock can be much faster because anyone can just grab it. Whoever gets there first gets to grab it and they can make progress. So probably the butcher sells more meat with an unordered lock, unless he loses all his customers because they're all upset, right? So it's a nice trade-off there. Hierarchical locks are a little bit different. Here, anyone on the same socket would be more likely to get the lock than someone on a different socket. It makes sense in an ordered lock in particular. There's a big cost to an ordered lock on a multi-socket machine. So a hierarchical ordered lock would say, oh yeah, we have some fairness within a socket, and then with some fairness between sockets, but it's not a total global ordering. Delegation, queue-based locks avoids this contention for a single cache line. You have, whenever you want to acquire a lock, you put yourself in a linked list, and you wait for your item in the linked list, and everyone waits on a different item. That way you're all spinning on local memory as opposed to some shared cache line, and that can really be helpful. Delegation and combining are these ideas that instead of every thread operating on its own, acquiring a lock and then accessing the shared data structure, you ask another thread to do the work for you. That way we have guaranteed serialization without acquiring any locks, and you can have real memory locality benefits. It can be more complicated to program, or at least it'll be different to program than a lock-based design. So that can be a big drawback. Lock-free data structures, I think, are usually best avoided, but they can be extremely fast under the right circumstances, especially when you have a lot of reads and not so many writes. So sort of the standard idea is you do all the work to make a change, but it doesn't actually show up in the data structure, and then you do a single compare and swap execution to put that work into the data structure. If you can design your data structure so that that's possible with a single compare and swap, then you can usually do a nice lock-free data structure. It's more expensive for the writer, it's a little more work to do this kind of two-phase thing, and if the compare and swap fails, you have to redo the whole thing, but it can be very beneficial on the reader side, make up for it. A huge problem in all of that is memory reclamation. So you want to free something. Now it could be there's readers that are still using that element, and so RCU was a good solution for that. Take a look at RCU again. Finally, on the data parallel programming side, I think we want to have a good idea of the sort of the overall programming model of vectorized code. So what is it that we do for both of these, both GPU and vectorized code, is this single instruction, multiple data idea. We're applying the same instruction to many different data elements at the same time. So if you have code that needs that sort of thing, there's the potential to do it in two different ways. One would be the standard vectorization instructions or vector instructions on the CPU. There it's very important to know that not all CPUs support the same instructions. Like moves are everywhere, but move DQA is only there on an AVX2 enabled processor. So how do we deal with that? Well, first you have to tell the compiler, right, that I intend to compile for this kind of target CPU. So you need to know what the CPU will have. So now the compiler produces code using those instructions. If you try to run it on some other CPU that doesn't have it, it'll crash. Alternatively, you could have code that you could compile code for lots of different targets, and then at runtime you can first ask the CPU what it supports using the CPU ID function instruction, and then you can decide from there which of your various compiled functions you will use now that you're running. It makes things complicated in that sense, but it can be worth it. So you want to look at the trade-off in terms of complexity for handling all of that, but also there's some performance trade-off in setting up for vectorized code. You need to set up your data structure correctly so that it can be quickly loaded into vector registers. And you need to fill vector registers and take the data out of vector registers. Usually it's worth it if you're doing a large array, let's say. If you have a tree with no arrays in it, you probably can't do it with vectors. So what's appropriate for vectorization is good to know about. And then general purpose GPU programming is this even more parallel version. I think that two key elements to know about is this fact that we're running lots of threads without any synchronization, or more or less without any synchronization. So shared memory, at least, there's no synchronization for it. And then that these threads are executed in warps or in work groups of some chunk, 32 being a common one, where they all run the same instruction. Or if they don't run the same instruction, well, now they're divided into further small pieces and it doesn't go fast. So basically we want work groups that all actually run the same instruction every time in order to go at the full speed up of this machine. In that sense, it's very much a SIMD architecture that we are saying, okay, add, and then it adds 32 different registers to 32 other registers, right? Quite similar to the way the Intel vectorization works for 8 or more. And there was some interesting and recent extensions to OpenCL that also supports. So OpenCL being the one that does data parallel programming on a CPU. It also has some interesting targets for GPUs. So you can kind of write SIMD code for a GPU with very little extra lines. Yeah.
That should be OpenMP.
Sorry. Yes. Absolutely. This should be OpenMP. Yeah. Yeah. Okay. I will, before I forget, I will change that. All right. So we are out of time, but since it's the last class, any further questions? Nothing? All right. Don't forget those evaluations, and I'll see you next Friday. Good luck with your exams.